This script for the set exercises will run k-means and GMM clustering on synthetically generated data. For the Gaussian mixture models, I use a fitGMDist function, which is a MATLAB built-in function, because if we had to do it from first principles, that would mean we'd have to make EM from scratch. But firstly, before explaining how everything works, I'll just show you that the code works, where various figures are generated that I will discuss later in the video. The compute distances here calculates Euclidean distances. It first initializes everything to 0, and then it loops through each center, and for each center it finds the differences between all the data points to that center, and then it calculates the distances essentially using the Pythagorean theorem. I also meant to mention how important this part is, which is the power to 2 operator, that is the squaring operator essentially, and it basically enlarges the differences so the algorithm pays closer attention to errors. Within cluster sum squares, that is the cluster errors, is calculated with compute WCSS. The WCSS variable will be initialized to 0, and then it will get the number of centers, which is all the centroids, the size of all the centroids defined, and like the size of how many, and then it will loop through all of that. And then the cluster points equals data assignments basically means you assign all the cluster points to that centroid, and then if that cluster is not empty, it will proceed with that, and it will therefore calculate the differences of all the cluster points to the center, and then it will calculate the WCSS from that, which is the WCSS plus the kind of like the matrix summation of the differences, which again squared because it amplifies it. Now for the data generation, I used generate Gaussian clusters, which creates 5 distinct clusters that are unequal in size, as defined here in points per cluster. That's like quite realistic, and the separation value of 6 places the cluster for separation far apart, as a circle roughly 7 units between neighbors is very strong for separation. And just to clarify precisely why it ends up as 7 is the cluster centers are placed on a circle of a radius of 6. If you put 5 centers evenly around a circle, then they're 72 degrees and they're 72 degrees apart each other. And when you work that out for the spacing from geometry, it comes to 7.05. So that means they are like clearly separated. And to ensure that the clusters were clearly separable, I placed their centers in a pentagon pattern using linspace, because that's 5, to get 5 equal angles, and then cos and sine to calculate the x and y coordinates for each center. And then finally, for each cluster, the points are generated using random here, which is standardly taught to us straight away, and this creates the Gaussian blobs. The line below pushes all the blobs to the centers where they should be, and the function also outputs the true labels. They're used to like ID the different clusters, and in this program I use like colors to distinctly identify which is which. Just before delving into find optimal k, I just want to say that I hard-coded k in as 5 to abide by the brief, and so it will always be k equals 5 when I'm actually clustering, because otherwise it could deviate from what we're allowed to do. Just so I don't mess up my talking, WCSS is within cluster sum squares. So what find optimal k does is it loops from k equals 1 to max k being 10, so it loops from 1 to 10. In the first iteration, it will get the overall mean, it will calculate the WCSS, and it will calculate the silhouette score. But this cannot apply because it's 0, because there's only one cluster and there's not other clusters to compare against, because it checks how close points is to its own centroid versus its neighbouring centroid. So beyond the first iteration, it will do k-means each time, and it will pass in the data, the k that's being used to test which is optimal. It will do 100 iterations per num run in num runs, and it will calculate the within cluster sum squares for the plots, and it will calculate the silhouette score for the plots. The silhouette score is the silhouette function. Is an evaluation metric function. So it's a built-in function for MATLAB, but since it's evaluation, it should be okay. K-means plus function is an intelligent initialization function that chooses its first centers at random, and then subsequent ones are picked probabilistically as square distances from existing centers. Figure 1, the dataset, that is a 4,500 point dataset split into 5 distinct Gaussian clusters. As we can see in the elbow method, the clusters get tighter and tighter until it flattens like an elbow after k equals 5. And in the silhouette analysis, we can see clusters become best separated as k equals 5. Therefore, both methods independently confirm that k equals 5 is the optimal number of clusters. This single run with k-means plus converged fast to WCSS of 9,045. But this run hit a poor local minima, as you can see by the elongated clusters. The bottom right chart shows centroid movement drops from 3.3 to near 0 by iteration 2 using the Frobenius norm, confirming convergence. Figure 4 here is the GMM results. Comparatively, both algorithms give identical pentagonal results. In conclusion, when data geometry satisfies k-means spherical assumptions, GMM's complexity offers no advantage. Thank you for watching my clustering demonstration. The code is inside the report and attached to the submission.